Okay, okay. So I'm very grateful for the invitation. It's very nice to be here. I'm from the Università of Padova. I concede that the Medici started the botanical garden 2 years before Padova, but our botanical garden is the oldest one in the world to be still in the same location, having the original layout. And the University of Padova was founded in 1222, so more than 100 years before the University of Pisa. But anyway, I'm very grateful to be here. My talk will be about processing of ceramic materials using additive manufacturing technologies. I will concentrate on the discussion on using liquid-based feedstocks, especially specifically from precursors. We work on polymer-derived ceramics, we work on sol gel-based materials, and we work also on geopolymers, all for additive manufacturing. So the reason why we are interested in liquid feedstocks is that powder-based feedstock for additive manufacturing have some issues in terms, for instance, of the stabilization of fine ceramic powders in a non-aqueous medium, photopolymer specifically. Also, if you disperse a high load of fibers in such a polymer, then you have a very high viscosity. You need a special equipment for printing if you want to achieve good results. But the main point is that, for instance, it's very difficult to print silicon carbide using DLP or optical-based technologies due to the absorption of the radiation. There are some ways around that, for instance, by slightly oxidizing the surface of the silicon carbide. But if you use polymer-derived materials approach, then you can avoid this issue. Also, if you're considering other technologies such as direct inviting, then particle size controls the nozzle dimension. A rule of thumb is that typically you need to have a nozzle size which is 10 times larger than the largest particle within the feedstock. Otherwise, you will get clogging of the nozzle. Of course, if you use liquid-based technologies, then you have some restrictions in terms of, for instance, the type of technology that you are using. If you can, of course, you cannot use binder jetting, for instance, because you will not be able to generate liquid layers. And for instance, there are some limitations in terms of the compositional range, and that is why we are using sol gel in order to extend the range of composition that we can obtain, for instance, to work with non-silicon containing compositions. And with sol gel, we can make, of course, both oxide and non-oxide ceramics. I don't want to preach to the choir, so I'm not going to discuss what preceramic polymers are. Let me just mention something that was already discussed by Professor Schafferner, meaning that when you process preceramic polymers, typically you work with thermoplastic materials that have the potential to cross-link to become thermoset materials, and you indeed need to have cross-linking before pyrolysis, at least for certain shapes and compositions, in order to avoid the softening and loss of shape from after making your structure. And I would like also to mention that ideally you want to have a high ceramic yield, and this means that if you start from 100 grams of preceramic polymer, you would like to end up with the highest amount of ceramic after that. And good preceramic polymers have a ceramic yield that can be as high as 98%, which is related to the molecular structure of the precursor. On the other side, let me also mention the fact that if you're using a preceramic polymer that has a low ceramic yield, you can still shape, and you can also convert that material to a ceramic component, and the advantage there would be that you increase the resolution of your part. So for instance, with additive manufacturing technologies, you have limitations in terms of physical limitations in terms of the size or the minimum feature that you can generate using additive manufacturing. manufacturing. For DLP, it's 50 microns, pretty much on the XY plane. And if you want to go beyond that, you can use a low ceramic yield preceramic polymer, and after pyrolysis, due to the high shrinkage, you can get much higher resolution. So I will be discussing only a few examples for specific technologies, and I would like to start from VAT photopolymerization technologies applied to pure preceramic polymers, specifically using digital light processing, which is a layer-by-layer type of technology. There are 5 different possibilities for achieving the shaping of ceramic components using preceramic polymers using this technology. And ideally, you would like to have a commercially available high ceramic yield preceramic polymer that contains reactive groups. There are some of them that have acrylic, vinyl, or epoxy groups that are commercially available, but they've been developed for other applications. So they have, for instance, linear molecular structures, and this means that the ceramic yield is very low. Or if they have vinyl groups, the reactivity is too low, and some people have proposed a Thioling click chemistry approach in order to speed up the fabrication and the reactivity of the system. If you're a chemist, I'm not, you can synthesize your own polymer, but we were the first ones actually to come up with the approach of generating components from a preceramic polymers using additive manufacturing. And we follow 2 different approaches. One is the chemical modification of a commercially available high ceramic yield preceramic polymer by grafting onto it photocurable moieties. The other approach is even simpler because we're simply blending a photocurable polymer, which can be either silicone or a fully organic material, with a non-photocurable high ceramic yield preceramic polymer. This sounds quite trivial and simple. You simply mix the 2 polymers, but actually it's not that trivial because you need to match the hydrophilicity and hydrophobicity of the 2 polymers in order to obtain a fully transparent and stable system. So here I'm simply showing the blending approach, and the reason why I'm simply showing that is that I want to go beyond and describe what we are currently doing in this field, so I'm not spending too much time in telling you what we did in the past. So we used photocurable siloxane acrylate that is used to generate conformal coatings on electronics. It's very highly reactive, but it has a very low ceramic yield because of the linear molecular structure. Or you can use, as I mentioned, a fully organic photopolymer. And we tested different non-photocurable preceramic polymers, and the best ones are the ones that contain phenol groups due to the hydrophilicity and hydrophobicity behavior that I mentioned before. And this is what we are currently doing. So we are using a volumetric approach for 3D printing ceramic materials. This was a development from a German startup in Berlin, Xolo 3D. In 2020, they published in Nature. We were the first laboratory in the world to acquire this printer. And having a volumetric 3D printing approach comes with several advantages in terms of the fact that there is no oxygen inhibition or layer rebuild necessary, so it's a very fast approach. You can see that the printing rates can be as high as 1 cubic centimeter per second, and high resolution are possible. And there is no stair-stepping effect because it is not a layer-by-layer approach, and this means that specifically for ceramic materials that you do not have a lot of defects at the surface. All the layer-to-layer interfaces correspond to weak points in a 3D printed part. There are also drawbacks in this technology, namely the fact that it comes with a very specific photoinitiator dual color system, and this causes some limitations in terms of the type of materials that we can use. The approach is as follows. You have your, this is your cuvette, and you have UV light coming from the side, you have visible light that comes perpendicularly to that, and the cuvette moves in this direction. Basically, you're projecting a movie, and you're building your part while the cuvette is moving. And the first wavelength activates the photoinitiator, and this generates an excited moiety that, together with the co-initiator, starts the radical polymerization process. So the issue is that this technology has been developed for conventional polymers. You need to have a system that is compatible with the proprietary dual color photo switchable initiator, type 2 photoinitiator, highly alkaline environment. The viscosity is very high. You need to have a polymer that is very highly reactive because you're printing within the volume, and you need to have enough energy to trigger photopolymerization. And you have to extract your printed part from a viscous system, so you need to be able to achieve strong and rigid parts. And the system needs to be highly transparent, of course, because you have to, the radiation has to go through the volume of the liquid. So we started working with Preceramic polymers. We also are working on with colloidal particles in order to make other compositions for ceramics, but I cannot discuss that because of proprietary work. And you can see here that the photopolymer, which is an organic acrylate, is highly transparent. If you start blending with the silicone, then you start losing the transmittance. And then, of course, if you increase the content of silicone, then you will have less organics to burn out, and you would have a higher ceramic yield. So ideally, you would like to work with high compositions, but then you have to deal with the transmittance. The higher content systems have a low transmittance, but we have some viable formulations that we can print. And you can see here that these are, of course, the parts that we wanted to print. This is Galileo's. He taught at the University of Padova for 18 years. And you can see that we can print quite accurately parts. These are all based on Preceramic polymers. You can see that because of the volumetric approach, we can print, for instance, directly bowling cage structures. And then after pyrolysis, due to the high content of organics, we incurred in some issues which are typical for Preceramic polymers, that is cracking due to the release of gas, mostly coming from the organic part. So we had to devise a way of achieving cracked parts, and we did that by adding some pore formers that would decompose before the decomposition of the urethane acrylate, generating a transient porosity that allows for the release of the gaseous components. And you can see that, for instance, in this gyroid structure, you can appreciate the quality of the surface and the lack of layer-by-layer features. Let me switch to different technology, direct writing, and I will also discuss now the additive manufacturing of ceramic matrix composites using this approach. So for carrying out direct writing, you need to have fluid that behaves like a Herschel-Bulkley fluid with an index below 1, so you have a pseudoplastic system that also has a yield stress. And you have to engineer your feedstock in order to provide that type of rheological behavior, because this means that after extrusion of your fluid, of your paste, then you can retain the shape that you have just given, because after releases of the stresses, shear stresses from the nozzle, the viscosity increases dramatically, and this helps keeping the shape of the part. So we started working with chopped fibers or short fibers based composites, and one of the features of this approach is that if you do things correctly in terms of the shear stresses which are related to the size of the nozzle and the length of the fibers, then if you do direct inviting, you align the fibers along the direction of the printing part. And so we were successful. We were actually the first ones to show this for Preceramic polymers. You can see that we can print good parts in terms of shape. This is before pyrolysis. You can appreciate the presence of the fibers within the material. After pyrolysis, of course, the matrix shrinks, but the fibers do not, and therefore we have some issues in terms. We had some issues in terms of cracking. This is also related to the interface, the forms between the matrix and the fiber. So, in order to modify that, we started adding silicon carbide particles to the Preceramic polymer, and this allowed us to pretty much eliminate the cracking after pyrolysis. There are still a few cracks, but it depends on how you process it. So now we can say that we can obtain chopped fiber-based silicon carbide-based systems in which the matrix is non-cracked with a single pyrolysis. Then the issue was, are we actually making composites or not? Meaning, do we have graceful failure? If you look at the fracture surfaces, then you can see that there is some pull-out, and you can see this is the position where the fibers were. You can see that we have a homogeneous distribution of fibers. We still have a little bit of voids due to the difficulties in mixing the system. But the point is that this does not necessarily prove that we have a composite behavior, because if you fracture such a material, you might simply crumble due to the fracture the matrix between the fibers, and this is not an evidence of graceful failure behavior. So we generated single filaments. We tested in 4-point bending the filaments, and you can see that actually we do have graceful failure behavior. So we have been actually able to generate chopped fiber, short fiber, reinforced CMCs. The next point was to go towards 3D printing of continuous fiber reinforced CMCs. We had a project sponsored by Kinetic in the UK, and we came up with a device that allows us to extrude continuous fibers. So we have the fibers coming down in this way. We have an inner chamber where we do the pre-preg while we are extruding the fibers. So this contains a silicone-based system, liquid system. Of course, we can use other Preceramic polymers. And on the outside, we have silicon carbide particles containing Preceramic polymer. And the fibers coming out, they also bring with themselves the matrix, or actually it's the opposite. You can see here, this is after pyrolysis. You can see here that we were able to obtain materials with a large content of fibers. You can see that we still have issues in terms of cracking, but this is unavoidable because while with chopped fibers, we can somehow arrange them during pyrolysis in order to achieve an uncracked matrix. If you have continuous fibers, you certainly have some sort of interface between the matrix and the fibers, and this leads to cracks that are perpendicular to the fibers, cracks in the matrix. So we will need to do further PIP, pyrolysis infiltration, and Preceramic infiltration and pyrolysis cycles in order to heal these cracks. But you can see here that with this approach, we have been able to achieve a dense matrix between the fibers. And of course, we have a lot of things still to improve in terms of the shape of the filament, and also in terms of the presence of residual voids that come from the fact that we are using highly loaded slurries to reduce the shrinkage, and they are difficult to mix, even if we are using the correct mixing devices for this type of pastes. Part of the fibers, part of the voids come also from the fact that we are applying pressure to the entire system, and it's difficult to have a gas-tight system that does not have the infiltration of some gas within the slurry while you're printing it. So we have developed a new approach just very recently, where we have a coaxial nozzle, and we are extruding the parts. In this way, it's very easy and it works well. We will still have the issue of cracking after pyrolysis. This is a pyrolyzed part. There are not many cracks, but this is due to the fact that we still have to improve the addition or the interface between the fibers and the filaments. So there are no cracks in the filaments because the interface was very weak. And this is related also to the fact that we didn't do enough pre-pregging of the fibers, so we are now modifying the setup in order to be able to print. We are also working, would you mind clicking on this slide, please? I mean, on this, yeah, see, please. It should have started automatically, but anyway. So we are also doing robotic arm manufacturing, and we have developed a system where we do actually UV-assisted direct writing. So while we are printing, we are irradiating the system that obviously contains a photopolymer, and we can do free-forming, and we can generate structures that you wouldn't be able to obtain using conventional direct writing technologies, like this sandwich with octahedral cores. And so you can see here that with this approach we can do free-forming. And we are also doing this with this approach, again, we can make, for instance, sandwich panels directly. And my colleague Georgia, she's been working with a CMC-based system with short fibers. And the issue here is that, of course, in order to cure the system, you need to have enough transparency to allow for the material to cross-link. So we cannot have silicon carbide powders that reduce the shrinkage in the matrix. But this means, that we need to do PAP cycles, and you can see that this is after third pyrolysis, and you can see that we are healing. We still have some cracks that need to be healed, but if you keep going, then the apparent porosity is decreased. So, in conclusion, you can use liquid feedstocks based on preceramic polymers, and I've shown you photopolymerization. We do DLP, we do two-photopolymerization, we do volumetric additive manufacturing, we do direct writing plus UV. We are also working on CMCs and the hybridization of different technologies in order to allow us to do free-forming. And this is the group and some of the sponsoring agencies. And thank you for your attention.
Thank you, Professor Colombo, for your presentation. Please, are there any questions?
I have a question for Paolo. You showed some pictures of the short fiber and also long fiber composite, and there were some cracks due to shrinkage stresses. Have you measured the fracture toughness in these materials, at least short fibers composite?
So, I mean, we have not computed the area underneath the stress-strain curve. But we just simply wanted to demonstrate that we do have graceful failure.
No, but I mentioned fracture toughness with when you
with a chevron notch.
Well, with a notch, yes, with a notch.
Yeah.
Yes, yeah.
So the filaments are 350, 400 microns. So I'm not sure chevron notch will be useful.
Well, chevron notch, yes, but just a notch, because in ceramics it's difficult, in fact, to cut a notch, yes, because they're very hard material.
In bulk ceramic samples, that the standard way of doing toughness measurements. On filament-based structures, I'm not sure it will be meaningful because you have the interface between the filaments that act as a weak point. So in theory, I guess you should do a notch that is larger than the filament, but you would still have within the notch the interfaces. So maybe.
Hello. Okay. I have the question that you use this 150 microns short fibers to do the work. How you avoid this agglomeration of this 150 microns short fibers before the process, because they tend to form fiber balls and so on. How you do it?
So this is one of the advantages of using a liquid-based approach, and we can use solvents that we can then evaporate, but we use planetary mixers that are very efficient for paste-based formulations. So I think we do not have a lot of problems in terms of agglomeration, as you could see from the cross-section of filaments. We do have still problems with some residual voids coming from the embedding of air during mixing.
Thank you.
May I ask also one question? To know if you are also thinking of investigating the usage of different heating sources for faster debinding, curing, pyrolysis step.
So not for these materials, but for instance, for zirconia, we can go from 3D printed to fully dense in 1 hour and 2 minutes. 2 minutes for sintering, an hour for chemical debinding. So we can do that with FDM-based systems, and also with direct invited, and also with DLP-based systems. Yeah.
Using
UHS.
UHS.
UHS. Yeah.
Okay. Thank you. One last question.
Do you have an idea for the fiber volume fractions that you'll be able to achieve with this technique?
So I have some ideas on how to increase that further. At the moment, we are at about the 20 volume range. For the continuous fibers, we can certainly go high. The reason for keeping at that level was to limit the fracturing for short fiber composites. For continuous fiber reinforced CMCs, we will end up with cracks anyway, so I think we can increase further the content of fibers, absolutely. The problem will be that we have the fibers in the core and they are not homogeneously distributed within the filaments, so we will try to reduce the shell size or thickness.
Thank you.
Okay, let's thank again Professor Colombo.